So in this video, we are going to be looking at the shortest path. Now, the shortest path between two vertices in a network is the path where the sum of the weights of the edges is minimized. So it's similar to a minimum spanning tree in the sense that we're looking for the smallest possible sum of the weighted edges. But what this sort of subtopic is asking us to do is looking at two vertices. How can we get from one to the other in the shortest possible distance or the shortest possible time? So we're going to jump straight into this because it is quite hands-on and intuitive to look at. Unlike minimum spanning trees, it's not as systematic. We don't have something like Prim's algorithm to make it easier for us to find. We just need to do a bit of trial and error and use some common sense to find this. Now, it's saying the shortest path between town C, so this guy over here, and town F. So we can see there's a couple of different ways we can get from C to F. One is to go from C to D to E to F, but I can already see here 6, 9, 7, that's kind of going to add up to something higher than if we'd taken some other routes here. So we are somewhat considering the smallest possible edges. So to get from town C to start working my way down here, if I went 5 and 4, that already adds up to 9, which is significantly shorter than this path that I had here. So I'm going to draw this in. I'm going to go C, B, E. And from here, basically, if I'd stopped at B and tried to go up to A, then to F, that would have been 7 plus 6. But here we have 4 plus 7. So this is going to be belonging to our shortest path. So our shortest path, we're going to label it. We're going to write it out in the same kind of form as we've done before. So we can say the shortest path is C, B, E, F. And the length of this shortest path is 7 plus 4 plus 15. So that is going to give us 16 kilometers. Now, the question doesn't actually ask for, question doesn't even tell us units. So let's just say 16 units. Question didn't actually ask for the length, but I just thought I'd write it in just so you can see that we're essentially just adding them like we've done before. Okay, in example 2, it's saying to find the length of the shortest path between the following vertices. So first I have A to E. So A to E. Now these are relatively close together. I basically have two different options I can take. I can go A to B to E or A to C to E. And I can see that 5 plus 7 will give you 12, 6 plus 5 will give you 11. So the shortest path here is going to be A, C, E. And that will give you 6 plus 5, which equals 11. They haven't given us units, so we can leave this as is. So for part B, I am going from A to F. So let's just rub this one out here. I'm trying to get from A to F. Now, I can, just by looking at it, there's only really one way we can kind of do that makes sense, right? We can go A to C to F, because all other ways will require me kind of backtracking and doing extra addition. This gives me a length of 12. The only other thing I could do was A to B to E to C to F, but we can already see that's going to add up to something a lot higher. Or if I went around this way, it's just going to end up summing to more. So I'm just going A, C, F. This A to C to F, which is 6 plus 6, which gives me 12. Next one, we're trying to get from A to G. So from here to here. Let's do it in red again. Okay. There are a couple of different options I can take, but mainly two that make sense. I can continue going down here. So I have my 12 plus 8, which would give me 20. Or I can go 6, 5, 10. That will give me 21. So the shortest path is A, C, F, G. So that's 6 plus 8, and that gives us 20. Okay. D, I'm trying to get from A to H. So let's just have a look. A to H. You need to get all the way from one side to the other. Now I can see that the path that I took up to G from before is 20 units, plus another 10 would give me 30. Now I can just check this with the other ones. So I can go 5, 7, that's 12, plus 10, 22, here 32. And this one here, that will give me 5 plus 14. That's going to give me 19. And then adding 12 to that will give me 31. So that's going to be longer again. So A, C, F, G, H, that's going to be my shortest path. So we go A, C, F, G, H. And to find that one, we're just adding all of them up. So 6 plus 8 plus 10 equals to 30. So there's a little bit of trial and error, but it's pretty simple addition we're actually doing to get from one vertex to another. Just one more example. It's saying here that Darcy has drawn a network diagram to represent several streets for traveling from his home to the shops. The numbers indicate the times in minutes. Remember, when we are given a unit, we should give our answer with the units written in. So here we are looking at the shortest path from the home to the shops. Now, there's a lot of different ways we can do this. We can see, if we look at this in two parts, okay, let's just consider this half of the diagram. Now, I'm going to be going somewhere from up here down to here. So I'm most likely going to pass through one or more of these vertices down here. Now, I can go either down here, so A to D to E, or I can go A, D, G to H. Or I can go A to B to E. Or A, B, C. There's a couple of different things we can do, but there is a little bit of trial and error we have to do. So you can pause the video and just have a go on your own, but we can pretty much see that if we take this particular way, we're just going to try a couple. If I do A, B, C, F, I, that's 5 plus 5, that gives me 10. If I try another one, we have 2 plus 1, that's 3, plus 5, 8, plus 3, 11. Okay, that doesn't work. 1 plus 2 gives us 3. If we go this way again, I get that same thing happening. I get 11. If I go 1, 2, then 3, that's going to be 6, plus 5, 11 again. 1 plus 3 gives you 4, 6, then 11 again. So the shortest possible way is this path at the top here. That sums to 10, while all the others sum to something higher. So the shortest path is A to B to C to F to I. And the time taken is 10 minutes. So that brings us to the end of the video and how we can use our shortest path in a network diagram. There is a little bit more trial and error than we've been doing up until now. It's less systematic, but there are typically options that you can rule out relatively quickly. We saw that quite a bit in these first two examples. But thank you so much for watching. This actually brings us to the end of the series. So thank you so much for joining me, and I'll see you next time.